All right, guys. So we're going to cover chapter 13 today, which is on fluid mechanics. It's kind of like a short chapter, so I'll probably go over it a little bit with you guys tomorrow, and maybe even start chapter 14 and continue chapter 14 on Thursday. So chapter 13 is basically on what we call fluids. So let's talk about what fluid is. One of the things we know, and we already kind of mentioned that earlier as well in the first few chapters, is that matter is normally can be classified to be in three states or three phases. So we have solid, which have a definite volume and shape. Let's say an ice cube, for example, or a box, right? Then we can have a liquid, which has a definite volume but not definite shape, like water. So let's say if you have a cup, right, or a container, you pour the water. So the water has a definite volume, but it doesn't have a shape. So it's going to take a shape of any type of container, right? And we have gas, which is unconfined, has neither a definite volume or shape. That means, it can be easily compressed. So if you have some kind of region with gas, and if there's some kind of piston, you can push it down and really kind of compress the gas into that much smaller area. So there's also actually a fourth one, which is known as plasma, and that generally happens when the temperature becomes so hot that atoms basically break down and you have electrons and the nucleus separate from each other. But not something we're going to be discussing anytime. So let's just concentrate on this, three different types of matter right now. And what we're going to do here is we're going to mostly concentrate on 2 and 3, because 2 and 3, liquid and gas, can actually flow. And fluid is a collection of molecules that are randomly arranged and held together by weak cohesive forces. Usually solids have very strong cohesive forces, and there's very this molecular bond between molecules in a solid is very strong. But in liquid and the gas, it's weaker, so they can actually flow. And the collection of, molecules, right, that can flow, either, keeping their volume like liquid, or just basically completely, randomly moving without any definite shape or size, which means gas. And that means liquid or gas together, combination can be considered as fluid. That means when we consider fluid, it's either liquid or a gas. And there are a lot of, important, let's say, application in physics where we will see that, let's say, fluids, right, are important. They're really important concepts, really important principles we're going to study in this chapter. But one thing I'm going to do in this chapter 13, I'm going to, right now cover the static fluids. Okay, we're going to only cover sort of like a static fluids, and either later on, if we have time, we might cover moving fluids. So right now, so this video here is going to be on, non-moving or static fluids, so sometimes known as a hydrostatic, or the fluid in hydrostatic equilibrium. All right, so one of the things we're going to talk about here is pressure. All right, so pressure is going to be very important for us in this chapter and the next few chapters. So one of the way we can kind of define, let's say, pressure, which we'll do in the next slide, we need to have a system where generally we're going to consider a little bit simplified version of the system. When we consider pressure, usually like in terms of molecules, there are sometimes way too many variables to keep track of. So let's simplify a little bit this fluid model of fluids. Let's assume that fluid we're considering always going to be non-viscous. That means it's more going to be always like water rather than like, let's say, syrup. Okay, and do not sustain shearing forces. That means, if you compress it, you're not going to break something. So let's say if you have a solid, if you compress it, you can break it. But in water or gas, you can easily compress without sort of like breaking them. So the only type of forces that can exist in a fluid is one that perpendicular to the surface, Because one of the things we can consider here is, let's say if you have a container and there's a liquid over there, or fluid, let's say. So the molecule of the fluid will be moving with some velocity. And then when it's moving with some velocity, it's then gonna hit the container with that velocity, right? So when it hits the container, oops. So let's say during the collision, when it hits the container, there's a force acting on the molecules, right? So let's say from the container, or you can think of it like this. When the molecule moving, when it collides with the container, it exerts force on the container wall, okay? So that means those are the forces, and you can see, right, it's perpendicular to the surface. Or when the molecule has a force acting on it from the container wall, which is action-reaction force, right? That also is perpendicular to the, let's say, container wall. Sometimes you might have a particle, for example, that is moving like this and hits the container wall with a force like that. Well, you take this and break it down into perpendicular to the container wall or parallel to the wall. And what we do here is we only assume that the one that is perpendicular is the effective one. So we're only going to be looking at that. That means the collisions, right, give rise to this force, okay? And the force, when it's acting on this sort of like an area of interest, so if you take this area over there, so for example, right, so you have a container like this, and you kind of choose small area A, and then when the molecule is moving and colliding with this and exerts a force F, then one of the things we can say here is that this force is the magnitude, right? The F is the magnitude of the force exerted by the fluid and or by the molecule on the wall, right? So here we say piston, but pretty much same idea. Where the A here is the surface area of the let's say area of interest, and the force is the action reaction force between the molecule and let's say the container wall. So then this ratio of applied force divided by the area is what we generally define to be pressure. That means pressure is nothing but force acting on some area A. That's why the units are newtons per meter square. Force newtons, area meter square. But we don't use this. We define this ratio of Newton per meter square to be Pascal. Okay, so then Pascal is the unit for pressure, and this is SI unit for pressure. Okay, so SI unit for pressure, that means every time we're calculating a value for pressure in any of the equations, we should be using Pascal as a unit, not even newtons per meter square, even though those are also in terms of the SI units. One thing we'll see that pressure generally has a lot of different versions as a unit. So, so one of the main used other units for the pressure here is the atmospheric pressure, because as I say, right, so the fluid, it can be gas like air or a liquid like water. So whenever you're considering, let's say the pressure due to the air molecules, then you are looking at the pressure at sort of like in terms of the atmosphere, right? So atmospheric pressure. Generally the pressure, even though it's force divided by the area, pressure itself is a scalar quantity. It doesn't really have a direction. It's a value at some point. So that's why, for example, if you have, let's say this is the surface of Earth, then let's say you have air molecules. See, close to the surface of Earth, air molecules are, relatively dense, right? There's like high concentration. Higher you go, it becomes less and less and less. So technically then the pressure here is increasing as you go down. So this is, let's say, P pressure. Let me put A for the atmospheric pressure. Sometimes also P0 for the atmospheric pressure. So that means that pressure is proportional to the magnitude of the force in that equation, right, that we saw. And the direction of the force producing the pressure is perpendicular to the area of interest. A large force can exert a small pressure if the area is very large. And the atmosphere exerts a pressure on the surface of Earth and all objects at the surface. That means air molecules collide with your body all the time, and they actually exert force on you. And that force is atmospheric force, right? Atmospheric pressure is 1.013 times 10 to the 5 Pascal. That means roughly 100,000 Pascal. But since generally the surface of Earth, considered like, let's say the reference, so like, let's say the sea level, right? Considers the reference, then this is sometimes also known as 1 atmospheric pressure or 1 ATM. Again, ATM is the units for pressure, and generally we use it for atmospheric pressure. So 1 ATM is equivalent to 1.013 times 10 to the 5 Pascal, which is the atmospheric pressure at the surface of Earth, or like at the sea level. So that's why, let's say if you go above the surface, if you increase your altitude, then the atmospheric pressure will decrease. It's actually going to decrease, right? As I say, right? So the pressure decreases. So closer to the surface is higher concentration of air molecules, higher pressure. You go out a little bit, toward this, towards space, right? Vacuum of space. Then pressure decreases until you get, no pressure. That means it decreases until it's zero. What does it mean when the pressure is zero? That means you reached vacuum of space. It doesn't necessarily mean it's going to be zero, because even in space, right, in vacuum, there are molecules, there are hydrogen molecules, right? But they're very, 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 few in between. That means, you compared to the density that we have close to the surface of Earth, you can say it's, approximately, completely negligible. You can approximate to be zero. All right. Now, the fluids also apply pressure. And one of the things we have here is the fluids have a pressure that increases with depth. Well, that means as you go down. Well, it's in a way same thing true also for the atmospheric pressure, right? It increases as you go down. But one of the things we have here is there are a lot more water molecules per unit area, right? Than, let's say, or unit volume than the air molecules. So generally the pressure of a liquid is much greater than pressure of the, for air, right? So one of the things we're going to do here is we're going to set up an equation where we can, in a way, calculate what will be the, the pressure at some depth inside a fluid. But one of the things we have here is that the pressure in the sea or lake, you can see, right, will increase with depth. Also for sea or lake, you technically have different waters, right? So lake is a fresh water, sea is a seawater, and the density for the lake, the fresh water, right, is always given, let's say fresh water as 1,000 kilogram per cubic meters. And generally the density for the seawater is 1,030 kilogram per cubic meters. So it's small difference, right? It's a very small, tiny difference, but we can technically sometimes include that. But if you let's say use 1,000 for ocean or sea, the difference is so tiny that for us solving problems, unless it's specifically you're told to use 1030, you can just basically use 1,000. And one of the things we have here is, for example, so let's say this is the body of water, lake or ocean, right? So let's say this is the bottom. So let's say that means here we have air and here we have water. And one thing we have here is then, let's say at the surface, if it is open to air, right? If it's open to the atmosphere, then pressure over there is equal to the atmospheric pressure. That means equals to 1 ATM. Okay. And as you go down, right, basically as you increase your depth, then the pressure here increases. It increases with depth. But we're going to derive an equations that will allow us to actually see that mathematically and calculate that. All right, so for now, just like atmosphere decreases with altitude, let's say atmospheric pressure decreases with altitude, then the water pressure increases with depth. And if the fluid is at rest in a container, all portion of the fluid must be in static equilibrium. Remember, one of the things I mentioned we are considering only fluids that are at rest. That means there's no moving fluids in this chapter. And all points at the same depth must be at the same pressure. That's another thing, you know, I'm going to actually use sort of like animation in a little bit where I can demonstrate some of those things. So one thing we're going to be able to see here is, for example, let's say if you are measuring pressure over here, then if you look at somewhere else, same depth, you know, this pressure 1, pressure 2, they will be the same because it's the same depth with respect to the surface. All right. And here's one sort of like, let's say, example I'm going to use to derive an equations for the, let's say, the pressure at some depth d. So think like this. So what we have here is we have a container with water, okay? And what I'm going to do here, I'm going to use just a sample of fluid. I'm going to just choose a sample of fluid, which is just this rectangle over here, okay? And one thing I have here is then, so let's say what I'm going to do, I'm going to do a little bit different. So I'm going to choose this sample of liquid that is kind of like this. That means it reaches the atmosphere right there at the top. Okay. So this is my, let's say parcel of water that I'm, or sample of fluid of interest. Okay. Now it has mass M, right? And you can see, right, it has volume V, right? Because it's kind of like I'm choosing a cylinder, sort of like a cylinder. So there's an area A over there at the top. So let's call this area 2 at the bottom, right? And what I have here is this. So I'm going to do net force for that parcel of water. And those are vertical forces. Now, one thing I have here is this. Well, this guy has at the top, there's a force, and it's atmospheric force. That means entire air molecules, entire atmosphere of Earth, pushing down at that, let's say at that surface area. That means there's the atmospheric force. But there's also another force, which is, this parcel of water, this volume of water has mass. Well, if it has mass, it means there's also a gravitational force. Kind of like, let me put it here. So like, let's say, right? So this was my parcel of water. So there is this force from the atmosphere exactly at the center of mass of this parcel, right? There is also gravitational force acting on it. That means I have also this force, right? But think like this, if I'm doing my vertical, let's say, force, net force, then atmospheric force is negative because it's down. Well, gravitational force is also negative because it's down. But think like this, if you have a container with water in it, you don't see that parcel of water, right? That sample of fluid speeding up down, accelerating down. It's at rest. That means there has to be another force balancing those two. And that force acting at the bottom, this area 2, at the bottom of that, volume of fluid, and this is air, water molecules, basically generating that force. So I'm going to say this is force at that depth D, which is upward, so plus F of D. And combined together, you get 0. Because it's, it's in static equilibrium, hydrostatic equilibrium. All right, so rearrange, we get this. F at that depth is equals to atmospheric pressure plus the atmospheric force plus gravitational force. That means when I have this parcel of water, right, those sample of water, the atmosphere pushes it from above, gravity pulling it down, but it's not accelerating because of this force at the bottom. And that force is able to balance it. That means it has to be stronger, than individual, atmospheric pressure, atmospheric force, or the gravitational force, because it's equals to their combined, sum. All right, so let's see what we have. So at the bottom, let me maybe use a different color. So at the bottom, so I have this area A2. And what I have here is, remember, what is force? Force is pressure times area, right? Remember, pressure is force over area. Rearrange, force is pressure times area. That means it's pressure at that depth D. And this is basically, I'm saying this is depth D with respect to the surface. So right now, ignore this H, right? So let's say, or do this. Actually, this, ignoring this D, we're saying the H is the height of that, of that cylinder. That means the pressure at that height H, that means area 2 is height H below the surface. So that means pressure times area 2 is equals to, then I have atmospheric pressure, sorry, atmospheric force is atmospheric pressure times that area 1, then plus the gravitational force, which is mass times gravitational acceleration. All right, so here's one thing we always do in this chapter. Every time there is a mass, we rather use density volume combination than mass. Remember this, mass per volume is equals to density. The rho here is density. And rearranging this, I can write mass as density times volume, right? And this equation is going to be used a lot. That means here I can replace this. So pressure at this H times area 2 equals atmospheric pressure times area 1, then plus, instead of mass of the water, I do then density of the water times volume of the water. This is basically volume, this volume over here, right? And then times G. All right. Now, one thing I have here is this then. pH times A2 equals atmospheric pressure times A1 plus density of water. But what I'm going to do here is this. So let's say if I have a cylinder, what is the volume of that cylinder? Well, you can see, right, volume is equals to the surface area times height, is basically area times height. That means I'm going to replace volume as area times height, then times G. Right. So now we are ready to completely simplify this and get our final equation. See, what I have here is this. This is my area 2 or area 1. This is my area 2. And then this area over there is some kind of like, general area of this parcel. And they're all the same. That means I can cancel the area 1, area 2, and this area. And what we end up with this pressure at this depth H, you can say, is equals to then atmospheric pressure, which is exerted at the top, then plus this rho GH. This rho GH, because here area after cancel, you cancel the area, you end up with the rho GH. And this is then the equation for the pressure at some depth H. That means you can then use this equation to calculate pressure at any depth, because you can see, right, this is the atmospheric pressure at the surface, and we know that it's just 1 atm, or 1.013 times 10 to the 5 Pascal. This is density of the fluid. It could be water, it could be oil, depending on what you have, right? This is 9.8, and this is then your height. That means you can see, right, this term here becomes bigger and bigger and bigger if you have a height which is bigger and bigger. Or that means if you increase the height, not depth, right? If you increase the depth, you are increasing the pressure, okay? All right, so again, this is, again, all the complete, breakdown of the equation. And this is our, pressure, okay? That means this pressure will be for fluids. Doesn't matter if it's a liquid or a gas. You can then calculate it. So one thing we can also talk about this. So let's say if you have a fluid and, for example, it's not open to atmosphere, then this guy here is 0. Okay, if it's not open, then this guy is 0. And then what you have here is at this, generally over there, what you will have here is you're gonna have a pressure of 0, kind of like a small vacuum. So that's why when you seal something, right, you basically create a little bit of vacuum over there. All right, so then what we end up is this. All right, so if a liquid is open to the atmosphere and the P atmosphere is the pressure at the surface of the liquid, then P0 is the atmospheric pressure. The pressure depends only on the depth H within the liquid. The pressure is the same at all points having the same depth, independent of the shape of the container. All right. And the change in pressure at the surface must be transmitted to every point in the fluid. And this is a very important, principle. Sometimes also, so it's a Pascal's principle or Pascal's law. So it says that change in pressure applied to an enclosed fluid is transmitted undiminished to every point of the fluid and to the walls of the container. So that's why, for example, when you open your, let's say, toothpaste, right? It's you have a liquid or fluid over there, right? That is in an enclosed container. So that's why anywhere you press for your toothpaste, right? It's gonna basically, that pressure, right, is gonna be transmitted everywhere within that toothpaste tube, and it's gonna come out, from the opening. All right, so this is, Pascal's law, and I have another example of that. But first, let's solve a problem, which is, to calculate the pressure 1,000 meters below the surface of the ocean. Again, remember, the ocean is technically salt water, and we should use 1,030 kilogram per cubic meters. But let's say for simplicity, we just use 1,000 instead of 1,030. So let's take the density as 1,000 kilogram per cubic meter, and the pressure is 101,300 Pascal. That's for the atmospheric pressure. So we're gonna calculate the pressure at 1,000 meters below the ocean, and then compare that pressure to the atmospheric pressure. See how many times it is, stronger, basically. All right, so it's simple enough, because let's say this is your ocean, this is the depth, right? I mean, we don't even know what it is. Let's say we don't even know if it's 1,000 meters below the ocean is already the, let's say, ocean floor. We just say that all we do here is we're going to choose some point P, and that point P is going to be 1,000 meters. So H is equals to 1,000 meters. Okay, it's open to the atmosphere, so let's say this is atmospheric pressure at the top. Then what I have here is, so sometimes even you might be doing this. This is P2, this is P1. Then you can say then P2 is equals to P1 plus then rho GH. That means you just choose 2 points, right? One at the surface, the other one is 1,000 meters below. All right, so this is then 1.013 times 10 to the 5 Pascal. Then add this to rho GH, so 1,000 kilogram per cubic meters, then times 9.8, then times 1,000 meters. Okay, that means pressure at that point 2 will be 9.901 times 10 to the 6 Pascal, which is basically 9.901 megapascal. That's part A. For part B, or when we're comparing, right? So the way you can compare is to do a ratio, pressure 2 over pressure 1. Well, this guy here is 9.901 times 10 to the 6 Pascal. This one is 1.013 times 10 to the 5 Pascal. Okay. Well, you divide them, you get roughly 100. That means it's 100 times greater pressure. Okay. What it means is this. Let's say if you try to dive to that point 2, what you're going to have here is 100 times pressure difference compared to that at that point or at that depth and at the surface. Remember, at the surface, we have entire atmosphere bombarding with us with this 100,000 Pascal pressure. That means from outside, all the air molecules hitting us with that pressure, but we're fine, nothing happens to us. That's because we also breathe that air, and we have that air inside of our body. That means that same air is basically pushes from inside as well. That means what we have here is, let's say this is us. See, there's a force from outside, but there's also force from inside. Okay, so like a balloon, right? So let's say force from outside, but there's also force from inside, and you're in equilibrium. They cancel each other. So that's why we are completely fine, at the surface of Earth, right? Because we have both air inside and outside, and there is no pressure difference. We're very small that, let's say nothing dangerous for us. But when you go here, when you, let's say, diving here, right? What you have here is inside your body, you still have air. Outside of your body, you have then 100 times, greater pressure from the water molecules. That means what pushes you inward is 100 times bigger what pushes you outward. So that means it's gonna, press you down. It's gonna, it's like, imagine like, you being pressed, how about that, with 100 times stronger force. So it's gonna, crush you basically. That's why, we cannot survive if you try to dive really deep. Our lungs will collapse and everything. So it's gonna be very difficult. All right, so even submarines, which are, let's say, still, the material that they use for submarines is very strong, but the biggest problem for humans or submarines is the pressure difference. All right, so this delta P pressure difference between those 2 points. It means inside and outside. Inside is still air, right? Outside is water. And what you have here is even the submarines, they have a limit, right? They cannot go, too deep because of that pressure difference will, destroy the submarine. All right, so one thing I'm going to do here is I have this kind of like the simulation that I want to, show you guys. All right, so here's kind of like nice flash simulation where you have a pressure gauge. Say that you are, at the surface of Earth, and you have like 1 atm. Okay, we can even make it like matrix system. So 101.3 kilopascal. And see if I go up, if I'm increasing my altitude, that number is actually decreasing. Okay, so I can't really go higher than that, but you can see, right? With altitude, it's decreasing. See, right now, I have let's say a hole where there is nothing there. You can assume it's air, but still, if I go down, you can see, right? It's actually increasing, because there are more air molecules over there. That means, what I have here is atmospheric pressure increases with depth, decreases with altitude. All right, so, but it's kind of like easier to see with the, atmosphere. But there's also English units, which is, we can use PSI for that. PSI is pounds per square inch, another unit for the pressure, pounds per square inch. And you can see, right, generally at 1 atm, you have then 14.6 or 14.7, right, rather, PSI. That means 1 atm is equivalent to 14.7 PSI. All right, so let's go back to, atmosphere. Here's then, or maybe like, atmosphere right here. It's easy to do it like this. So here's what I have then. I'm gonna fill this guy with water all the way. Now what I have here is, remember how the atmospheric pressure would decrease. So actually, let me do this. So let's say if I have just all, air molecules, right? If I go to the 3 meter depth, you can see, right, pressure in ATM barely changed. It's, 1.000004. So it's, a very tiny change. So let's go back over there. Now fill it with water. And what I have here is, now if I use the second gauge, so we can compare, see by how much it changes. It changes by a lot. Now it's like, 1.5 times almost, atmospheric pressure. So you can see, right, because of that area now is fluid, it changes with depth. And now you can use that same equation that we did before to calculate, you know, the atmospheric pressure. So if I use the same, that equation that we had, right? So if I use, you know, pressure at this point 2, let's say here's point 2, is equals to pressure at point 1, which is would be here, point 1, right? So plus rho GH. So replace rho with 1,000. You can see, right, 1,000 kilogram per cubic meter. Replace H with, you know, 3 meters. And, you know, if you use this, like, let's say 1 ATM, right? So you're going to calculate this. So if you're using kilogram per cubic meters, and if you're using meters, right? So this is actually going to be in Pascal, but then you can convert it to ATM and then add this to this one. That means you can add those together, or both of them converted to ATM. You will get this number over there. Okay. So now, what I have here is you can see, right, density 1,000. So if I have more dense, so let's say, okay. So if I have more dense, you can see it increases the pressure for the same depth. If I have less dense, then it actually decreases. So you can see, right, let's say I have a gasoline, which is 700 kilogram per cubic meter, and the pressure decreases. It's still greater than atmospheric pressure, but it's less. If I go honey, which is more dense than water, then pressure actually increases compared to water, okay, which is 1,000, you know, kilogram per cubic meters. All right, that's good enough. All right, so another thing I want to mention here is this. So let's get rid of all this water. So let's say I have this type of, you know, container. One thing you can see here is I have kind of like an irregular shape, right? I have on the left side, look at the shape, and on the right side, but they are connected at the bottom. So that means when I start filling this up, you can see, right, both of those fill out together, and at every time they have the same water level. And this will be true as long as both of them are open to the atmosphere. So you will have, you know, basically same thing. As you can see, right, it goes all the way. And one thing I have here is, so technically I have two containers, one on the left, one on the right. See, if I use this pressure gauge and measure the pressure at 2 meters, see, I get 1.19, let's say. I go to the other side, 2 meters. You can see, right? Yeah, basically I have exactly same thing, 1.19. Okay. And the same thing is here. That means once you measure pressure at one point, so let's say if I measure the pressure at this point, 0.1, and if I draw a horizontal line, everywhere on that horizontal line, pressure is the same. That means this is pressure 1, this is pressure 2, let's say this is pressure 3, somewhere over here, pressure 4, they're all the same because they're all on the same horizontal line, okay? So that's kind of like the interesting thing about fluids that, you know, so that's why, let's say when you go to a doctor and they need to get a pressure of your heart, they don't measure, they don't have that, you know, equipment wrapped around your, you know, let's say your chest, right? They do it your arm when you're sitting. Why? Because your arm at that level, right, is the same horizontal line as your heart. So when they measure the pressure at your arm, they're measuring pressure basically at your lungs or your heart and things like that. All right, so anyways, one thing we can also talk about before, let's say, we finish this. So let's say if I have some kind of unknown liquid, right? So one thing I can do here is, let's say, take this pressure gauge, measure the pressure at, let's say, 2 meters. And now that I have pressure, use that pressure equation to calculate the density of this, you know, unknown fluid. Because what I have here is this, right? So let's call this, let's say 0.2. I have pressure at 0.2 is equals to pressure at 0.1 plus rho GH. Pressure 2 is this pressure gauge. Pressure 1 is this pressure gauge. G is 9.8 if it's earth, right? H is 2 meters. The only thing is unknown is density. use this, calculate density, and then you can tell me what type of fluid it is. Okay. All right. So let's go back to our lecture. Okay. So one of the things, I want to talk about, and this is application of a Pascal's law. So this is a lot of times when, let's say, you take your car to a mechanics, let's say car mechanic and things like that, they have this, let's say this setup where they put your car, let's say somewhere, and so let's say there's like some kind of like an area, right? They put your car, and then they, with your foot, they press something, and then the entire car goes upward. So this is basically uses the, the concept of Pascal's law, which is the pressure. This is known as hydraulic press, okay? Because what we have here is that over there you have a confined fluid. Let's say here there's a piston with area A, A1, and there's another piston with area A2. How much force you apply to area A1 is F1. And then what you end up getting, F2, is the output force on the other side. And one of the things we have here is the pressure at point 1 is the same as pressure at point 2 because the fluid is confined. Fluid has the same pressure anywhere inside this, confined area. So that means for point 1, you do F1 over A1, and this will be equals to F2 over A2, which is pressure at point 2. That means one of the things we can do from here is the output force, F2, is then equals to the ratio of A2 over A1, then times force 1. That means, for example, if you apply 10 newtons force, then how much your output force will be, it depends on the ratio of the areas. So that's why generally what we do here is we, let's say, choose this area 1, where you, let's say, apply your foot, where you is very small, so maybe like 1 square meters, where area 2 is very large, so let's say 100 square meters. And what you get here is this ratio gives you 100 times 10 newtons. That means you get 1,000 Newton output, even though you only push with a 10 Newton force. As you can see, right, you can get much, much amplified output force because of the area differences. All right, so here's an example. So in a car lift used in a surface station, compressed air exerts a force on a small piston that has a circular cross-section and a radius of 5 centimeters. So that's basically your, the first one. This pressure is transmitted by a liquid to a piston that has a radius of 15 centimeters. Now here's the second one, and it's a radius of like 3 times more, radius. Okay. So one of the things we want to know here is basically what force. So let's assume that, let's say this is area 1, this is area 2, and let's assume, let's say you apply some force F1. And what we do here is when we apply force 1, then we get the output force of, let's say, roughly 13,300 newtons. Because if there's a car over there that weighs 13,300 newtons, that means the gravitational force acting on it is that much, right? By applying force of 13,300 newtons as F2, you will be able to lift it with constant speed. So what should be then the input force? So we get that. So basically that's part A. All right, so then what we do here is we understand this is a Pascal's law, application, F1 over A1 equals F2 over A2. That means I can solve for A1, which is then going to be A1 over A2 times F2. Now, the areas, those are circular areas, right? So we circular cross-section areas, that means it's pi times R1 square. This guy is pi times R2 square. And this one here is F2. All right. I can cancel the pi's, and what I get here is this. So this is 5 centimeters square. Well, this one here is 15 centimeters square. I don't even have to convert units because it's a ratio. And this is times 13,300 newtons. All right, what we get for F1 here is 1.5 roughly times 10 to the 3 newtons. That means it's 1500 newtons. So what you get is about 10 times more force as an output force when you do that, all right? Okay, so that's for part A. And for part B, it's asking then what will be then the pressure anywhere inside, right? Remember, the pressure is the same. Well, I can use either P2 equals F2 over A2 or P1 is equals to F1 over A1. So might as well, let's use this. So let's say this is 1500 newtons. We just calculated this, divided by pi times r square. Here I need to convert to meters. So it's 0.05 meters square. And what we get here is 1.88 times 10 to the 5 Pascal. All right, so that's then the answer for part B. All right, so as I mentioned, a lot of times what's important here is pressure difference. So the pressure difference is the dangerous part, right? So whenever you're considering, let's say, pressure between 2 points or pressure between inside and outside, right? So then when you're using this equation, let's say P2 is equals to P1 plus rho GH, then what you have here is then you look at, move this P1 to the other side, so it becomes P2 minus P1. Again, this is pressure difference delta P. And you can see, right, this is equals to then rho GH. That means pressure difference always going to be equals to rho GH. All right, so here's what we get. So a lot of times P2 is known as absolute pressure. Okay. And P1, again, if it's open to atmosphere, right? If you're considering that P1 to be the boundary between some liquid and atmosphere, so this is, let's say, the atmospheric pressure. Anyways, then what we can see here is then the difference between absolute and atmospheric pressure, right, is known as a gauge pressure. So this is then a gauge pressure, okay? So the gauge pressure is equals to this quantity that we call rho GH, okay? So then rho GH is then sometimes known as a gauge pressure. That means equation here is absolute pressure is equals to atmospheric pressure plus gauge pressure, or you can say then the gauge pressure is the difference between absolute and atmospheric pressures. So when you take one of those tire gauges, right, and you measure the tire pressure, you're not really measuring the pressure inside your tire. What you're measuring is the pressure difference between inside and outside, okay? That means pressure inside minus pressure outside is what that pressure gauge measures. It gives you the pressure difference. All right. The last thing in this chapter that we're going to go over is the buoyant force. And this is a new type of force. This is a force that is always present in fluids, either liquid or gas, but generally is very, very weak, very, let's say almost negligible sometimes for air. We still can use it sometimes when you're considering, let's say, air balloons and things like that, but it's very, very strong in liquids. So one of the examples, think like, let's say you take a beach ball, you take the beach ball and you push it inside your pool or water, right? And when you let go, instead of the beach ball to sink, it's actually seems like pushed upward, right? So who pushes it upward? Well, it's a water pushes it with this, what we call buoyant force, okay? So it's the upward force exerted by the fluid on any immersed object, okay? So again, imagine a beach ball sized parcel of water beneath a water surface. So because this parcel is in equilibrium, there must be an upward force to balance. So this is a little bit different. So imagine, so let's say if you have a container, well, let's say a container with water. And what I'm gonna do, I'm gonna assume that if you think of if you look at this container with water, is water inside accelerating or not? Well, obviously not, right? Just sitting there still. Well, think like this. I take some imaginary parcel of water. Okay, so just that. Well, this parcel of water, let me just small sample, of that water, right? Well, it has a mass, right? So mass of that, fluid, let's say. Well, it also has a volume, right? So some kind of volume of that fluid. Well, think like this, if it has a mass, that means gravity acting on that, parcel of water, right? Then there's a gravitational force acting on it. Well, then how come it's not accelerating down with the gravitational force acting on it? Well, because the gravitational force is not alone. There is also, so let's say, assuming that all the mass is concentrated at the center of mass, well, there is also a buoyant force upward. So FB, and let's put it like that. Like you can see over here, right? So this FB basically acting on it, and that force is always upward. It's always toward the surface, basically. Okay. So just like when you pull this one inside, right? You push inside, you let go, the beach ball will be pushed upward. Okay. So that means at that instance there is a gravitational force, and there's this. Well, let's use B for that, like buoyant force. Okay. Now, why did then, let's say, the beach ball is pushed upward? Well, because buoyant force will be then stronger in this case than the gravitational force. So you're going to get overall acceleration upward. So it's pushed upward. It doesn't mean that every time the buoyant force will be stronger than gravitational force. You take a rock, do the same thing. You push it inside the water. You let go. It's not going to go upward. It's going to be then, sink and go downward. But you still have that. It's just this time the gravitational force stronger if it's a rock, so it's going to then have a generally acceleration down, and it's going to sink. So we're going to see there's like a little bit of tug of war going on inside. But the idea here is that, so even if you consider a beach ball or some kind of imaginary parcel of water, you can always assume that there is this upward buoyant force, okay? And if let's say you want more visual, view of that, just take something, put it inside, your bathtub or something like that, let go, and you will see it will be pushed upward. All right. So now what we get here is then you can say that there is this net force, right? So there's a net force that acting on this object. And one thing we're going to see here is, let's say from the next slide. So this is known as Archimedes Principle, generally. Okay. So Archimedes was the first one who actually recognized that there is this, upward push from the fluid. Okay. So it says the magnitude of that buoyant force. Okay. So magnitude of the buoyant force on an object always equals the weight of the fluid displaced by the object. Now, what does it mean? Well, what it means is this: if you have a container with water, so let's say this is the level of water, right? When you have nothing, then you take some kind of object and you immerse it fully in water. What does it do to the water? Well, it will increase the water level, right? It will displace some fluid. And Archimedes basically tells us that the buoyant force will be then in magnitude always equals to the weight of that fluid displaced by the object. That means if I take that displaced fluid, put it on a scale and measure its weight, buoyant force is equals to that. Not the entire water weight, but the one that has been displaced by, by this, the putting the object inside water, okay? Only when you put the object immersed completely inside water, how much water it displaces, then the buoyant force in magnitude equals to the weight of the displaced fluid. Okay. So with the beach ball underwater, the buoyant force equal to the weight of the beach ball size parcel of water. And it's much larger than the weight of the beach ball, which is, something is also important. Now, here's what we have. When you have a container with some water, okay, so let's say you put the beach ball, okay, you put the beach ball over there, immersed fully. What it does, it displaces some water. And we collect that water, we find its weight, and then we can say that buoyant force that was acting on this, beach ball is equals to the weight of that displaced fluid. that means it's equals to mass of that fluid. Again, only the one that is displaced times G, right, is equals to that. Okay. Remember, this buoyant force should be equal to the weight of the beach ball, right? Like BB, like beach ball. Why? Because see, the beach ball has its gravitational force. Remember, the gravitational force is the same as weight, right? So that means, let me put it like this. So there's this weight of the beach ball acting on it, and then the buoyant force. See, if the buoyant force is equal to the weight of the beach ball will just be there inside water, just sitting there stationary. But it doesn't do that, right? It is pushed upward toward the surface. Why? Because this force is greater, so then overall you have a net force upward. So it can only happen if the buoyant force is greater, it's larger than the weight of the beach ball. In this case, it happened to be greater than that. All right, so now, how about something else? So for example, you have the water, right? And I'm gonna put, let's say same volume. So let's say this is the beach ball, right? Exactly same volume, same size basically. But this time not beach ball, but let's say a bowling ball. Obviously, bowling ball, well, it's also BB. So let's say just bowling, let's say ball, right? Obviously, it has much greater weight than the beach ball. Okay. But how about the buoyant force acting on this bowling ball? So let's see. See, if I put the bowling ball inside water, it also displaces, some of the fluid. Okay. So now it displaces some of the fluid. Does it displace more fluid because it's heavier? Well, it doesn't. That's the interesting thing about it. How much water is displaced? That means if I collect this water, right, this water fluid, right, it's exactly same as before. How can that be the same then? How can the amount of water that is displaced be same for bowling ball and beach ball? Remember, we're assuming they're the size, their size exactly the same. That means volume of the beach ball is equal to the volume of the bowling ball. But obviously the mass of the beach ball is much smaller than mass of the bowling ball. Okay. But here's the thing. How much water is displaced has nothing to do with mass of the bowling ball or the beach ball. How much water is displaced only depends on their volume. Okay, only depends on their volume. So that's why even though the bowling ball is much heavier, it will still displace exactly the same amount of water because it has the same size, same volume. That means this buoyant force is same as before. But obviously now the weight, right, for the bowling ball is much greater because it's much heavier. And this guy here is now going to give me, net force downward. Okay, overall downward net force. Okay, so that's the interesting thing about this, because magnitude of the buoyant force on an object always equals to the weight of the displaced, the fluid displaced by the object. Okay, and the weight depends only on the volume of the object. That means you can always say this: volume of the displaced fluid is always going to be equal to the volume of the object. Okay. So that's kind of, one of the things we always going to be able to say. Okay. So now, it says consider a solid cube immersed in a liquid. So again, we have gravitational force and the buoyant force. That means this is basically what we kind of, looking at already in the previous slide. So in a way, what we get is the pressure at the top of the cube causes downward force, F top A. The pressure at the bottom of the cube causes an upward force, P bottom A. And then the resultant here is this. You can see, right? Buoyant force is equal to the, well, it doesn't look like the equation for the weight of the displaced fluid, but it is. Because here's what I have. buoyant force is equal to the weight of the displaced fluid. And weight is mass of the displaced fluid times g. But remember, I said that mass every time in this chapter will be replaced with the density times volume times g. And you can see, right, this is nothing but that equation over there. That means buoyant force is equal to the density of the fluid times g times the volume of the displaced fluid. That means how much it was displaced. So, okay. And volume of the displaced fluid always equals the volume of your object. That means if I have an object that, you know, has a regular size shape, I can find its volume. That means I know how much displaced, how much volume of the water was displaced. I can plug it into this calculation and calculate the buoyant force. All right. So that's, you know, one of the ways we can kind of, you know, calculate and do that. Okay. So let's stop here for a minute and go back. Okay. So we're going to go back to the simulations, but this time I have a different one for the buoyant force. Okay. So here's what we get. See, I have two objects, a block of wood and another, you know, a block that is basically, you can say concrete, right? Both of them are 5 kilograms. But you can see, right, in order for the block of wood to be 5 kilograms, it has to be much bigger. See, if I make them same volume, right? If I make them same volume, the wood is much, much lighter because, you know, it is just less dense, okay? So that's why what we get here is, let's talk about, you know, same volume for now. You can see that we're given here the 100 liter as the level for the water, okay? And one of the things we have here is, if I take the wooden block, right? See if I completely immerse, see now, it's gonna be pushed outward. Okay, so let's try again, push it all the way outward, down, so I'm fully immersed. Look at how much water is displaced. 105 compared to 100 before. That means 5 liter was displaced. Now let's try to, you know, basically the concrete block. And this is basically 10 kilograms, 5 times heavier. But if I take it and I immerse it, see again, 105 liters, exactly same thing. That means you get same amount of displaced fluid. All right, so push it back. Now let's do the same mass. For the same mass, water, the wooden block has to be much bigger, right? So let's do this. If I take then wooden block and I fully immersed, see now it's 112.5. Take it back, that means 12.5 liter was displacement, was how much the volume was displaced. Now take the second block, and this is just 102.5. That means just 2.5 liters displaced. You can see, right? Even though they're the same mass, you have only, you know, 2.5 liter displaced because it's much smaller in volume. You can see, right? Then displaced fluid depends on the volume of the object, not mass. And bigger the volume of the object, more water will be displaced, because that means if I want to know what is the volume of this wooden block, well, its volume is equal to exactly how much volume of the, let's say, water was displaced. That means it also equals to, you know, 12.5. All right. So now let's talk about then forces. Let's say buoyant and gravity. So let's say wooden block is 49 newtons. Okay. That means, see, when I immerse completely, its weight doesn't change, right? 49 newtons. But see, buoyant force is 122. And remember, we talked about, right? It's much stronger for less dense object, because right now, if I let go, see, it is pushed upward until it reaches equilibrium, right? That means now it's partially submerged, and the forces of the, you know, buoyant force and the gravity, you know, balance each other, okay? That means anywhere inside, right, when it's fully submerged, buoyant force will be stronger. Okay, buoyant force will be stronger for the wood. Now here we have another object, right? The second object. See, the weight is 49 newtons because it's 5 kilograms, but look at the buoyant force, 24.5. Why? Because it displaces very little volume of fluid, and because it's less than gravitational force acting on the, let's say, for this block, it will then sink because gravity is stronger, so it pulls it down. All right. That means in a way what we have is this. So when I'm considering, let's say, if the object will float or sink, it pretty much comes down to this: buoyant force minus gravitational force. Which one is greater? It will then be, determining where the object will go. Buoyant force is stronger, it will float. It will be pushed upward, will float. Gravitational force stronger, it will be, basically pulled down, it will then sink. Now here's what I have. Buoyant force, mass of the fluid, times G times volume of the fluid, minus, and this is gravitational force, which is mass of the object. Sorry, yeah. All right, so I did a mistake here, so let me do this. All right, so let's try again. So it's mass of the fluid times G, because the weight of the displaced fluid, minus gravitational force, mass of the object, times G. Okay, so if I continue, see, I can factor out G, and I have then mass of the fluid minus mass of the object. But what I'm going to do here, I'm going to rewrite this in terms of, so mass of the fluid is density of the fluid times its volume of the fluid, then minus, then density of the object times volume of the object, right? Remember again, mass over volume equals density, or, mass equals density times volume. But remember one of the things I talked about, that volume of the object always equals volume of the fluid. This is always going to be true. That means I can come back and technically rewrite this as both of them, either V fluid or V object, because they're the same. And I can then factor out this as well. That means V minus F of G is equals to G times V object. And all you get is this, density of fluid minus density of the object. That means you can see, right, it's all about the density differences. If the fluid, that means if the fluid has higher density than the object then will have a greater buoyant force, then it will be pushed upward, and it will be then, floating. Okay, but if the object has greater density than fluid, then it's going to then sink. So that's why, let's say this guy here has a higher density then, because it's probably a rock, right? I think its density is like, several thousand, like 3, 4, 5,000 compared to 1,000 for water. That means it has so density of rock is greater than density of the water, so it sinks. Here we have wood, and density of wood is less than density of water, so then it basically floats. So that means it pretty much depends on the density of the object and the water. Sinking or floating pretty much depends on that. All right, so one last thing I want to mention here is another way that we can find buoyant force. Okay, for example, and here's what we can do. Let's take this object here. Say it's 5 kilograms. I put it here on a scale and find its weight, 49 newtons. Then I put a scale inside water, so I put it here inside water and find the scale. I get 24.5. That means what I get here is 49. Here is 24.5. And that means what I have here is this. Buoyant force is equal to the weight outside minus weight inside, which is sometimes known as apparent weight. See, this is apparent weight because it's not the actual weight of the object. It appears to be that. So actual was 49 newtons. Then apparent here is 24.5 newtons. That means what we get here is this buoyant force is then 24.5 newtons, right? And you can see right here, buoyant force, it is 24.5 newtons, because buoyant force is the difference between actual and apparent weights. That's one of the easiest way you can also find the buoyant force. Weight something in air, weight some same thing in when it's completely immersed in water, and then their difference, right? Actual weight minus apparent weight will give you then the, let's say, the buoyant force. Okay, so the same thing I can do for the second block, right? So let's say it's 2 kilograms, for example. I put it here. It's 19.6. Okay, that means actual weight is 19.6. Okay, put it here on the scale. All right, it doesn't work for this guy because I guess too light. Okay, but okay, it doesn't work. It didn't work on this one, but you know, for the previous one, basically the same idea. All right, so let's go back then to the lecture to wrap this up. All right, so this just basically talks about what I just mentioned in terms of, you know, if you have, let's say, right, if you have the buoyant force and gravitational force acting on an object, so you have F of G and you have the buoyant force and it's fully immersed, then it's end up being the B minus F of G, which is, you can see, right, is just in terms of the tug of war between those two forces, right? It's nothing but the differences in their densities, right? So whichever has larger density wins, right? Water has a larger density, buoyant force is stronger, it floats. Object has a higher density, gravitational force wins, and it sinks. Okay, and that's basically what we have. Object density less than fluid density, it is floating. Object density greater than fluid density, then it sinks. Okay. One thing you probably have noticed in that simulation here is when I submerge the object partially, it doesn't then, the displays same amount of fluid as it did when it's fully submerged. Well, obviously because some of the water here is, or some of the object is not in water. And this is basically for partially submerged objects. We can calculate then how much water was displaced using this ratio, where the ratio of the displaced fluid over the object's volume, and here volume of the displaced fluid is not equal to the volume of the object. It's not equals to, it's only equals to when it's fully submerged. Then you can use this ratio to calculate. Okay, that means you can say V displaced is equals to density of the object over density of the fluid times volume of the fluid, volume of the object. And that's a ratio, then the equation will give you how much water was displaced. And it's not equal to the object volume anymore. Okay. So it's sometimes, it's fraction. Sometimes you might have, you see just a little bit and then most of it may be inside. So some of those icebergs and things like that, when you see in Antarctica, so you see an iceberg like this, but then, underwater, you might have maybe like 90% of that iceberg actually. Okay, so last example here in this chapter. So we talking about this Archimedes, who, if you don't know Archimedes, basically search him up. He technically considers the first engineer, the father of engineering, because he's the one who invented water pump, invented the screw, and this guy lived, I think over 2,000 years ago, 2,500 years ago, even maybe, like in city Syracuse, which is now the Italian basically city Sicily, I think, or in the island. All right, so the Archimedes was very famous. It was very smart, very famous, probably the smartest person in his kingdom at the time, and it was a Greek a colony, right, a Greek city. So you can see, right, it was asked to determine whether a crown made for the king consisted of pure gold. That means the king had a crown made of pure gold, but he had his suspicions that maybe the blacksmith, cheated, cheated, and crown is not pure gold. Maybe some of that, gold was stolen, replaced with some cheap material and things like that. So he had to figure out how to solve this problem. And it's easy to, let's say, if you put the object's mass, let's say, find the volume, right? And this ratio gives you density. And if this density is not of the, let's say, gold, that means, that's it, right? Because here's what we have. If I have one piece of gold and another piece of gold, doesn't matter, bigger, right? Say this is mass 1, volume 1, and this is mass 2, volume 2. And here's the thing, maybe another one is like this, or kind of like this, like, circular, like a spherical. So mass 3, volume 3. Well, if it's gold, if all of them are gold, if I take mass 1 over volume 1, mass 2 over volume 2, mass 3 over volume 3, you're going to get the same thing. The ratio is the same, even though the mass and volumes are different. So that's why he was very, he could have easily, let's say, find the mass and volume and then use that to compare it to another piece of gold. The only problem is, look at this crown. It's an irregular shape, irregular size. You cannot find the volume of that. So he basically struggled in terms of how to find the volume of that, until he one day realized that when something that you probably always notice but never really put together in terms of this type of application, is that when you let's say in a bathtub, right, when you go into the water, right, the water level goes up, and water level that displaced fluid is related to the volume of your body, right? Or when you take object immersed in water, that volume of the displaced fluid related to the volume of the object. But he was able to figure out this and make a connection. So that's why, according to a legend, he solved this problem by weighing the crown first in air and then in water. Suppose the scale read 7.84 newtons when the crown was in air, actual weight, and 6.84 newton when it was in water, apparent weight. What should Archimedes have told the king? Well, remember, if you have the actual weight and then apparent weight, their difference gives you the buoyant force, right? That means 7.84 newtons minus 6.84 newtons gives me 1 newton as a buoyant force. Now, what can buoyant force give us? Well, we know that buoyant force is equal to the weight of the displaced fluid. That means it's equal to the weight, which can be written as density of fluid times volume of the fluid times G. Well, as we just talked about, right, in a way then, volume of the displaced fluid will always be equal to the volume of the object, even if the object is any irregular size or shape. That means what all we had to do from here is use this, find the basically volume of the fluid, right? And then we could pretty much, find the, let's say this gold. Okay. So then we can do that by, remember, so if you're looking at the density of the crown, right, it's equals to then the mass of the crown divided by the, for example, the volume of the crown. Now, there are several ways of doing this problem. One of the ways, is on the slide, the lecture notes, and I'm going to show you the second one. So here you find the volume of the fluid. Okay. So if you find the volume of the fluid, then this will be then basically buoyant force over density of the fluid times G. Remember, this is water, so you can kind of, use that to figure out, right? So you can find the volume of the fluid, which means you have volume of the object, or in this case, the crown. Okay. And if you have this, then you can use the weight of the crown, which was actually 7.84, divided by the 9.8 to find the mass of the crown, right? And then if you have the mass, and then you have the volume, plug in here and calculate that, which is then the density. Or you can kind of rearrange everything here. So density of the crown here, mass of the crown over volume of the crown. All right, so, and what we can do here is basically then multiply both sides by, see if I multiply this G over G, I'm multiplying just by 1. Nothing changes about this, okay? So, but here what I end up with, mass of the crown times G is just the weight of the crown. Here is weight of volume of the crown times G, okay? Well, remember one thing. So in this equation, if I rearrange and write, B buoyant force and divide this by density. So let me see. So if I keep volume of the fluid times G, and this is equals to buoyant force over density of the fluid. Okay, and since volume of the fluid is same as volume of the object or crown, that means volume of the crown times G is equal to this ratio. That means here volume of the crown times G can be replaced with buoyant force over density of the fluid. All right. Anyway, so that's one, in a way, this is, one of the ways we can do that. Probably the first method is easier to find volume of the fluid, which is the volume of the crown, to find weight of the crown, from the weight of the crown, find the mass, and then plug in and use this. But you can also do that. So here what we do is, if you continue, right? So it's going to be weight of the crown times density of the fluid, then over buoyant force. Okay, and density of the crown here is equal to 7.84 newtons times density is 1,000 kilogram per cubic meters divided by the buoyant force, which was 1 Newton. So what we get here is 7.84 times 10 to the 3 kilogram per cubic meters. Okay, that means what the Archimedes was able to found is the 7,840 so 7,840 kilogram per cubic meters as a density of the crown. Now that wasn't a good news for the for the guy who made it, because density of gold, right, is roughly 19,000. So I mean 19,000. Let me double check that. Yeah, so it's 19,300 kilogram per cubic meters. I mean, it's not even close, right? It's 19,000 compared to let's say 8,000. Okay. So most of the gold was basically stolen and replaced with the cheaper, less dense material, which, it's hard to notice, right? But definitely, mathematically, right, you should be able to easily calculate that. All right, guys, so that's it for this chapter. Again, I'm only going to be looking at stationary, hydrostatic equilibrium, which is concept of buoyant force, pressure, atmospheric pressure, gauge pressure, and Pascal's principle.